last time we talked about SE and SD. We realize this is the elastic compliance under constant electric field, and this was the elastic compliance under constant dielectric displacement. And we now we're trying to cover what this actually means, constant dielectric displacement. Normally we may not think about this like constant dielectric displacement, and the reason because we actually get charge. And didn't I say charge was, charge was the over area was the dielectric displacement? I said that. So we need to clarify what we mean and why this is actually constant dielectric displacement. And it's constant dielectric displacement within the material. So we'll explain what this means. So we said last time, when we apply a stress to the material, we get a dielectric displacement. I explained this earlier. But now I'm gonna have to get into signs because we're gonna have things interacting. So let's just take a 2D object to make things easier on us. So we have this material, and we apply a stress to it, right? So we get charges on the top and charges on the bottom. But one side has to be positive and one side is negative. And we'll explain the mechanism for this in a couple of lectures. We'll do that. So there's a positive negative side. So let me ask you a question: which side gets the positive charges, and which side gets the negative ones? Well, from the information I gave you, you don't have any idea. But let's assume positive stress, or positive is tension. Okay. And let's assume that we're using a coordinate system which goes up. Up is positive. This is our coordinate system. This is also positive. So this is positive, and this is the coordinate system. So, and then we also have to define what an electric field does. So let's say we had an electric field applied to it, and we would have X equals dE. Right? So when we apply an electric field, we get strain. But what is positive and what is negative? So I'm saying when we apply a positive electric field with regards to this, coordinate system, then we get positive displacement. And we'll get into this anisotropic stuff later. But this is just to understand what these kind of subscripts mean. So when you do a positive electric field, we get a positive displacement. So the material expands. So we use a positive electric field, the material voltage is positive, so the material expands, or also stress is positive. So what this means is that what the material wants to do, or the charges which are developed on the material, are actually opposite. Because instead of pulling the material, instead of using an electric field, a positive electric field, to pull the material apart, and this is a very subtle point and it's very important to understand, so please be very attentive at this point. When we are stretching the material develops. Look, I'm going to write it down, it's so important. When we stretch the material, charges develop. These charges develop in such a way that the electric field created by them wants to return the material to the original configuration, to the original configuration. So basically what it means is, okay, I have the material, we apply a stress, right? Or rather, stress is X, capital big X. So the charges are appearing. Remember we said this is the coordinate system? The charges are appearing such that they're causing a reverse field in the material. They're causing an electric field like this. And this is a negative electric field. We'll call this ER for E reverse. This is an electric field which wants to bring the material back to its original position. See, normally we think about D E equals X, right? But this D is negative. This is a negative number. So we're going to get a negative strain, right? But so this kind of electric field is developed such that it wants to bring the material back. You stretch it out, and there's some charges coming in, and say we want to make everything go back. So this is a subtlety, and this is why in the future this coordinate system will be developed. You know, materials will be are oriented. It's called they're polarized. And we'll learn about that soon. But for now, I wanted to help you explain that this is actually like a negative electric field going on there. But it's a variable, so you don't really write negative. But there's a negative electric field going on. Now we'll introduce why is there constant dielectric displacement in the material. Why? Alright. So I mentioned that, look, here's the equation for dielectric displacement. I'm claiming that it's constant. Plus dx. It's really important to know these little simple things. Plus dx. Okay. And I told you that in the last lecture, I told you at the very end, I said that the electric field induced in the material, you know, so for example, in this situation, the electric field induced is equal to d x over epsilon. And because of this coordinate system here, this reverse field is negative. It's a negative field. Plus, and that we write epsilon plus dx. And what happens here? What happens? These cancel out. And what happens? What is this? What's going on? These cancel out. So there is a constant dielectric displacement within the material, although there is not a constant, you could say, apparently a constant dielectric displacement outside the material. So this equation holds. You know, this equation holds, although it doesn't hold in the material itself. But you know, sometimes we're not really that concerned about it. But you know, for the scientific sake, you know, measurements, and we like all of our, you know, stuff like that. You know, we like these little signs. So now you understand what constant electric field is. Electric field of the material, because the charges are on the top and bottom of the material, they're the same. So they're gonna keep the same electric field because there's the same potential. We always hold the same potential over it. And a constant dielectric field in the material, when we are pulling it, let's say, there's positive charges developed here, but this causes a reverse field. Right? We mentioned there's a reverse field going on here due to the effect of the charges. So therefore, within the material, because we have dx, because due to the pulling, we get some charges going on, and due to the you know, negative reverse field, we get these effects canceling out. Alright, thank you for watching.